Okay, how are we all doing? This is Mike Johnson here, and we're going to start up our discussion again about the way that we describe and qualify numbers. So, in our last video, in our first part, we discussed some of our earlier topics, which we see here, which were imaginary numbers versus real numbers, and then breaking down the dichotomy of real numbers into irrational and rational values. However, there are some further subqualifications that exist. So let's go ahead and discuss those. We'll discuss those in this next portion of the video. So once we have an irrational values, we're over here in the real number portion. Once we have an irrational value, then we know that we can further subqualify this, and we can do this in a very unique way because rational values can be broken down further. However, not all rational values have to be broken down further. Not all of them can be broken down further. So just as a quick description, this does not necessarily have to exist, this next category. So rational values, I'm going to put this little term here, they may, that's supposed to be a may. Let me go ahead and make sure that says may. So rational values may be broken down into this next category. And this next category are our category of integers, is our category of integers. And integers is a term I'm sure we've heard quite often going through any math, physics, and science course. And a lot of times I know when I was growing up, as I said before in some of our previous videos, that integers was a term that I used. However, I really didn't know what I meant by the term integers. So I use it often incorrectly and with hopes that I was using it correctly, but I did make a couple mistakes, I'm sure, growing up when describing integers. So the way that I like to describe integers, I'm going to show you how we look at integers in terms of a set. So I'm going to describe integers as a set. So down here in these prior definitions and categorizations are from the last video, but let's go ahead now and talk about integers in terms of just a set. When I say a set, I'm going to describe it in such a fashion of using these brackets like such, and I'm going to write these three periods here, and these three periods that are here, they actually are ellipses. And when we see ellipses in math and physics and science, they indicate that we are trying to find a pattern to recognize by looking at these next values. So I'm just going to go ahead and define it like such. I'm going to say that we have these three ellipses in the set of -3, -2, -1, 0, 1, 2, and 3, and then we're going to keep going on further, indicating by these ellipses. So I'm just going to make a little note here that these are ellipses. So these are ellipses. And those are grammatical terms, and they say how can we identify this pattern? So for some of us this may be easier to do than others, but let's go ahead and look at the positive side. So if I start here in the middle, if I start here at the middle at 0, and I move to the right, I see I have a value of 1, then 2, then 3. So I want you to think to yourself, even though this value is not written to the right, can we all guess that this is a value of 4? And then the next value after this would be a value of 5. And then the next value would be 6 and 7 and 8 and 9, all the way out to infinity. That this is never ending. This pattern continues forever. And then on the negative side, if we start here at 0 and move to the left, we have -1, -2, -3. On the negative side, this would be a value of -4, and then -5, and this would also continue out to negative infinity. So this pattern continues both on the positive and the negative side. So we often don't have to write these numbers, but we want to identify this pattern. But when we look at this pattern, we recognize that these integers are a special type of rational value such that they have no decimal additive. They have no extra portion of a fraction, that they are perfectly, they are perfect, and they don't have any extra added portion of a fraction. So for example, if I wanted to ask you, is the following, so let's go ahead and scroll down a little bit. So we'll say, is the following an integer? Whoops, an integer. So is the following an integer? So this would be just an example. And let's say I gave you -7. Oops, let's get rid of that comma. Let's say that I gave you +8. What about 2.3? and then square root of 10. So if I were to ask you about these individual questions here, are the following integers? So notice I flip often between lowercase and capital letters. I don't know why I do that. But if we recognize here -7, yeah, -7 is definitely an integer. It continues on in this pattern that we see above. +8 is also an integer. So if we keep going after 5, we'd have 6, then 7, then 8, and that would go on to +infinity. Down here, 2.3. Ooh, let's look at 2.3. 2.3 is not an integer. This is not an integer because of this 0.3. It has this small fractional additive to it at the end. So this guy, 2.3, is definitely not an integer. He is definitely not an integer. And then square root of 10, and if we analyze square root of 10, if I scroll back up here and then over to my left, and I look at that process flow diagram, that when I look at square root of 10, square root of 10 is an example of an irrational value. So since square root of 10 is irrational, there is no possible way that it can be an integer. So in this circumstance, this process flow chart definitely can help me understand how to qualify all these different values. So hopefully that gives you an idea of what integers are. So now I'm going to go ahead and I'm going to discuss about these further opportunities of integers to be subqualified. And if we want to further qualify an integer, which we don't necessarily have to do, or we cannot necessarily do, is we can do so in such a way we call these whole numbers. And I know growing up that I often interchanged whole numbers and integers all the time. So these can be interchanged as well. And then lastly, we can go through and qualify whole numbers as naturals, as natural numbers. So these are all mays. These are all may. They do not necessarily have to be qualified, but they can be if they fit the criteria. So before, when we looked at numbers, when we looked at the way that we defined our numbers, we know that this was a must, that a number must be imaginary or real. And you also learn later on about transcendental numbers, etc. But for right now, we can safely assume that all numbers are imaginary or real. And then we looked at all real numbers; they have to be irrational or rational. In these sets down here, these are our mays. They don't necessarily have to. So I'm going to go through down here, and we are going to discuss how to further go ahead and describe integers. So let's go ahead and describe, not integers, let's go ahead and describe a whole number. So let's go ahead and describe whole numbers. And I'm going to do so using the set notation that I did before. And it is actually very similar to, they are very similar to integers. They are not necessarily the same. Some may be the same, but specifically they're not. So whole numbers, I'm going to do it in a set that includes 0 and goes all the way out. That's a bad bracket there. That's a bad bracket too. There we go. That goes all the way out to positive infinity. So in this circumstance, these are my set of whole numbers. These are my set of whole numbers. That they are my set of whole numbers, and that is the only way that I will be able to have my whole numbers, is by looking at these positive integers, including 0. So whole numbers are a category of integers, and they exist simultaneously. So I'm going to ask a true and false question. So I'm going to ask a true and false question down here. So this will be true and false questions. And these are often pop up all over the place. I'm going to say all whole numbers are integers as the first true and false, and the second one, all integers are whole numbers. So let's look at this first one. If I look at this first one, this is declaring that all whole numbers are integers. So if I were just to quickly go through and look at my number process flow chart. So I realize that these can be broken down into imaginary, and then I have reals. Reals can be broken down into irrational. I'm going to abbreviate this. And then rational. Notice I'm just doing this briefly and quickly. And then here I have integers. Here I have wholes. And then here I have natural. So I just took about 15 seconds to write down a quick overview of that chart that I wrote prior. This first one says all whole numbers are integers. So notice here I have whole numbers. All whole numbers are integers. Yes, because in order to be a whole number, it first must be an integer. So in order to be a whole number, it must be an integer. So this, in fact, ladies and gentlemen, is a true statement. All whole numbers are integers. Let's look at the next statement. All integers are whole numbers. So let's think about this. Do all integers later on qualify as being whole numbers? Are they all qualified as whole numbers? So let's look at the set of integers again. So let's just look at that brief set of integers as we wrote it before. So here I start at -3, -2, -1, 0, 1, 2, and 3, and I have some ellipses here. Then I have some down here as well. So now if I look at the whole numbers, as I said, were the set of positive integers including 0. So notice -3, -2, -1, these guys are whole numbers. However, these guys are integers, excuse me. These guys are integers. Are they whole numbers? No, they're not. They're definitely not whole numbers. So are all integers whole numbers? False. They are definitely not, as we see here. -3, -2, -1 are integers. They are not whole numbers. However, all whole numbers must be first integers, because if they weren't integers, they could not be whole numbers. So again, this is the math play on the words here. And then in the next last 30 seconds of this video, let's go ahead and describe natural numbers. So I'm going to describe natural numbers, and I'm going to do so in the same set notation. So here I'm going to describe that, and I am going to describe them in such a way that you can see it. So let's go through and notice, what is the major difference between whole numbers and naturals? The only difference is that whole numbers, I'm going to write it here, whole numbers include 0. So the way that I remember it, a whole has a hole in it, and that way I know that whole numbers differ from natural numbers because whole numbers include 0. So natural numbers are a subcategory of whole numbers, and as we show that here, that all natural numbers must be whole, but not necessarily all whole numbers are natural numbers. There's only one difference, and that's going to be with the value of 0. So what I always recommend for people to do, is that I always recommend, especially my students, to go ahead and try your best to dictate this chart right here to memory, because it definitely makes it easier to break them down and categorize them whenever it comes down to test time, or if you're taking the SAT or the ACT or the GRE or the GMAT, it definitely makes this much easier to understand. So again, if you guys have any questions, you're more than welcome to let me know. Otherwise, I wish you the best with your studies.